Hello, Maths 1325 students. Let's finally begin calculus. And calculus begins from limit and continuity. What is limit and what is continuity? That's the topic here. And let's begin with a motivational example here. Let me expand the graphs a little bit. All right, we are looking at two graphs here, blue graph and the green graph. Blue graph looks pretty much okay. We have all those continuity except at x equal to -4, possible breaking, and x equal to 3, we do have a breaking. Now look at the right hand side graph, green graph. Mostly okay, except at x equal to -2, we have the split. And x equals to 1, we do not split, but either way, and the graph is blowing up to positive infinity. Otherwise, it looks okay. And here we have to consider something called point property, which is basically the property related to just a single point, versus local property. The property is related to not just a single point, but all the points around it. There are infinite many of them. The closer, the better. Let's go to this example here. Let's look at x equal to -4. What is my function value at x equal to -4? That y-coordinate is right here, the solid dot. This is emptied out, so this is just a placeholder. This is not part of the graph. This one is. And that's 3. How about f of 1? Well, right here, f of 3 is equal to 1. X value is 3, y coordinate is 1, function value is y coordinate. That's what I can see from this blue graph. And then how about the green graph? G of -2 is undefined. Nothing here. And if there were any point somewhere, then that will be my point, my function value. And how about G of 1? Also undefined. That's what I get from the second graph. And if there were any dot somewhere here, then that y-coordinate would have been the function value. But then again, these are point properties. Just looking at a single x-coordinate value and a single point. Now, what if we consider local property? That means not just a single point, but all those points, infinitely many points around it. Let's look at x equal to -4. Close to x equal to -4, overwhelming majority of points are down here. The closer, the better. So pretty close to y-coordinate of 1. Around x equal to 3, let's consider all those x-coordinate values around x equal to 3. When x is less than 3, then all those points are up there. Greater than 3, then all those points go down here. So to the left-hand side, we have up here. To the right-hand side, we get down there. So we have this necessary breaking. In this case, if I just move this point and fill this hole, then we have a continuous graph, no problem. Here, if I move this point up there, that's not going to help much, because local property already gives you breaking. Left-hand side, the right-hand side are very different. Here, left-hand side and right-hand side are behaving the same. It's just that point property, x equal to -4, that's behaving rather weirdly. So if I just move this point and fill it up, no problem, no singularity, just as continuity, fine. But here, there's no way out. Similar thing is going on here. X equals to -2. Well, that single point is not very important. To the left, blowing to positive infinity, blowing up to positive infinity. To the right, going down to negative infinity. See that? around x equals 1, to the left, to the right, both are going up to positive infinity. So those are local properties, not just a single point, single x-coordinate value, but we are looking at infinitely many. So calculus is a big quantum leap from point property to local property. So we have a huge conceptual leap going on here. So not just a single number, not just equality, but we have to consider other points around it. We use these kind of expressions. Limit as f of x, a function value, converges to L as x approaches to c. Or equivalently, limit as x approaches c, f of x is equal to L. This expression and that expression are equivalent. They're the same. What exactly does it mean? Y-coordinate, function value is y-coordinate. Remember, this is y-coordinate. Y-coordinate is getting closer and closer and closer to L. I'll show you the graph in a moment. One-sided limit, c minus, that represent to the left, c plus, that represent to the right. Remember, in number line, minus is the left direction, and then plus is right direction. And left-hand side, right-hand side, they are the same, then the limit exists, and that common value L. If they are different, these two are different, then there's no way we're going to get this limit. So undefined. And moreover, not just these two, but also the function values are all the same, then we say the function is continuous there. So we have all these explained perfectly there, but the problem is, it's really hard to understand what is going on here just by looking at these formulations, even though they are perfectly correct. So let us try to solidify our understanding through graphical expression. And there's a nice problem. Expand the graphs. Okay, all right. Here we have these problems. F of -4 limit as x is approaching to -4 minus and a -4 plus, and then just -4. How do they differ? Well, let's look at this one. This is just a point property. This is not calculus, no limit. When x equals to -4, function value is y-coordinate, so read the y-coordinate value. That's 3. That was easy. By the way, this is expunged, this is emptied out, so this is not part of the graph, this is just placeholder. The real graph is up there for this particular point, and this is just a single point. So just reading the single point is following the point property. But that's not what calculus is all about. Calculus is about local properties. You have to consider not just a single number, but infinitely many numbers, all those numbers around it. Let's look at x equal to -4, and let's consider all those x values close to -4, but a little bit less, 4 minus. So do you see this little negative sign there? That means left-hand side. So we are looking at x coordinate value close to -4, but coming from the left. So if I follow the graph, I have to follow this way from the left. And the function value is y-coordinate. So which y-coordinate do we get to? We get closer and closer and closer to y equals to what? 1. Is that clear? So this y-coordinate value, or this limit value, has to be 1. Now let's do the same thing to the right-hand side. For plus, so this is right-hand side. And I'm approaching to -4 from the right-hand side like this. So that's equivalent to following the graph from the right-hand side. And which y-coordinate do I get closer and closer and closer to? The same thing. So these two values are the same. They're both 1. So the limit is well defined, and that common value is 1. You can answer like this. So basically, following the graph from the right-hand side versus following the graph from the left-hand side. Which y-coordinate do we get closer and closer and closer to? Same y-coordinate value. So that common value is the limit. So here we go. Left-hand side limit, right-hand side limit, they're the same. So the common value is the limit. But this limit is different from this function value. Therefore, this function is not continuous. It's discontinuous at x equal to -4. Can I make it a continuous function? Yes, I can. By moving this point and move it down here and fill it up. In that case, this becomes 1 as well. So all the same, so we have continuity. Now let's go to the next problem. At x equal to 3, so right here, something interesting is happening. Otherwise, they're all continuous, all generic. For example, if I go to x equal to, say, 1, around here, no breaking, to the left, to the right, the same y-coordinate value, about 1 and 1/3. If we get closer and closer and closer to -2, right here, x equals to -2, y-coordinate is all merging to -1, so no problem there. X equals to 3, that's a potential problem. X equals to -4, that's another problem which we just went through. Okay, at x equal to 3, what do you have? The function value is 1, this y-coordinate value. This is just a point property which has nothing to do with all the other x-coordinate values nearby. Now let's consider the left-hand side limit. So this one, whoops. How do I get back? Okay, sorry about the mishap. I got back to where I was. This one we considered already. So let's do this one. So left-hand side limit. X is approaching to 3 from the left-hand side. So x is approaching like that from the left-hand side. 3 minus, so a little bit less than 3. Now if I follow the graph, I'm following this way. And that y-coordinate is 2. Now how about the right-hand side limit? Well, I have to approach from the right-hand side, which means I have to follow this portion of the graph from the right-hand side. That gets closer and closer and closer to y equals to -1, and that's this value. 2, -1, they're different. So this limit value does not exist. In order to have continuity, they all have to exist and they all have to be the same, but these two are different. That one is still different. This one is not even defined. So we don't have continuity, we just have something messy. We have a jump. We have a discontinuity. And that's discussed here. Now finally, this problem, determine all x-coordinate at which f is discontinuous. Explain why. Clearly, at x equal to -4 and x equal to 3, we have discontinuities right here and right there, otherwise all continuous. And the reason, well, the reason we discussed those. A and B, those are the reasons. A is a reason for -4, B is the reason for x equal to 3. So we answered all these. So whenever we have those jumps or some breakings or some emptied points, we do things like this. Follow the graph from the left-hand side or the right-hand side.